Well, thank you very much,
One
Nosson,
second, one
for.
second. Hello and welcome to the New York City Category Theory Seminar. We have once again the honor of having Ross Street talk about the core groupoid can suffice. Take it away, Ross, please.
Well, thank you, Nosson, and it is rather a sad day to have just learned yesterday that Marta Bunga, we've lost her. So this talk is actually, there are some ideas here that go back to her thesis. The idea of Morita equivalence for categories was her thesis involved that, and the idea of what I call modules, which is also called profunctors, that she didn't name back in that thesis. And she also did other work on Morita equivalence. So it's not completely unconnected.
Well, she did her thesis under Peter Fried, technically, right?
Peter Fried, yes, and well, yes, and Bill Levere
was there.
One of her supervisors. No, it's not going ahead. What's happening? Oh, there. No, we've gone too far. Okay, back. Well, see, the general problem is I have a commutative ring, and I'm going to let script V be the category of R modules all through this talk. And the category, and we've got another category F. And we're interested in the representations of that category F, which are just the functors from F into the category of R modules. And we call those R linear representations of F. In the case where F is just a one object category in which everything's invertible, you've got a group, and that's the category of R linear representations of that group. So I'm interested in categories F, just ordinary categories, for which there's a groupoid, such that the categories of representations are equivalent. And one way of getting a groupoid out of a category is to just cut down to keep the same objects and cut down to the invertible morphisms. And that's called the core groupoid. And the core groupoid, if you change the category F by splitting idempotents, then you don't really change the representations. So it's still the same category, it's equivalent category. If you pass to the idempotent completion of F, and yet, of course, that will change the core groupoid. So that's why I don't say that it's only the core groupoid I'm interested in, but in each case that all the examples I have, that's what the category will be. So the first thing is to linearize, which is just taking, as in David's talk last week, was it? We take the free category on a free, first of all, you take the free R module on a set. And if you do that on the homsets of a category, that gives you an R linear category or a V category with homs enriched in V, which I'm calling RF, where R was the commutative ring. And RF is now, it's actually the free R linear category or free V category on F. So that if you look at the V-functor category, that's the additive functors from RF into V, then you get the same category, except of course, when I write square brackets RFV, I'm thinking of the additive functors or the V enriched functors, and thinking of it as a V category, an R linear category. So that category of representation, it's just the same category of representations, really. But in those terms, there's a difference what you mean by Morita equivalent. For two categories to be Morita equivalent, just as categories, it just means that they have the same idempotent completion. But when you ask whether our linear categories are Morita equivalent, that means that well, there's this thing called the Cauchy completion, I call it, but it's what you do when you do the idempotent completion, followed by adding finite direct sums, and that's the Cauchy completion in the R linear setting. So if RF and RG are Morita equivalent as V categories, that means that I'm saying that the groupoid G suffices to capture the representations of F. And in the paper that Steve Black and I did on Dold-Kan-type theorems, so the main Dold-Kan theorem is the equivalence of simplicial abelian groups, say, with chain complexes of abelian groups. So in that case, you're not replacing the simplicial category by a groupoid, you're replacing it by a chain of arrows, whose consecutive composites are 0. However, in that paper, we showed that you could always reduce the types of theorems we were looking at to a groupoid suffices type situation. So in that original Dold-Kan equivalence, when you do that reduction process to change it to a groupoid suffices type situation, the F that pops out is not the simplicial category. The simplicial category has as objects the finite non-empty ordinals and the order-preserving maps between them. So this thing I call delta bottom is the category of finite non-empty ordinals and first order, well, order preserving and first element preserving functions. And if you look at the groupoid in there are the invertible things are, well, first of all, the invertible things are all endomorphisms, and the endomorphisms that are invertible are just identities. So the core groupoid in this case is just the discrete category with countably many objects. So the Dold-Kan theorem amounts to the equivalence of simplicial objects of V with a countable product of copies of V.
If one looked at the delta bottom, simplicial objects, geometric realization of simplicial objects on that, I mean, yes. What type of topological spaces do they describe?
Oh, what topology? Oh, well, the simplicial objects, it's actually the category for actions of, what is it? I can't describe it as a topological space. I mean, you're taking the geometric realization of the thing.
Right.
All right.
Okay. Never mind.
Yeah. So these are simplicial. Augmented simplicial objects.
No, they're special types.
There's a long story about this. I mean, I spent most of my life studying the simplicial category, so it's too long a story to probably go into.
Okay, never mind. Sorry.
Now, so let's take that category, delta bottom. I've got this notation where when I write a category with just one object next to it, it's the Hom monoid, the monoid of endomorphisms in that category. So delta bottom of C is the, I'm taking C to be the ordinal 3. So in delta bottom, the 0 is important. Anyway, that little monoid only has, I wanted to look at this example in a bit of detail because it does bring out most of the points I want to make. And these are, I mean, these things are in the literature, particularly I found out since Ben Steinberg's been telling me about the monoid point of view of all these things. But I'm just trying to give a categorical point of view today. Anyway, this monoid has 6 elements. I'm writing functions. The input is at the top and the value is at the bottom. So there's the identity function iota, sigma naught is what's usually called sigma naught, or in Gabriel Zisman it's called sigma naught. In the simplicial category, it's the thing that takes naught to naught and 1 to naught, and then everything else to the same. And sigma 1, as it's written there, Tor. Upsilon's actually the product of, which order is it? Upsilon's sigma 1, sigma naught, if I compose in the way we do in category theory most of the time. And zeta is actually a 0 in this monoid. It's, if you compose it with any of those other maps on either side, you get the same, you get zeta again. And the presentation of the monoid, sigma naught, sigma 1, and Tor are generators. And you have these identities, some of which are just telling you that zeta is a 0. Zeta is sigma naught, sigma 1. Anyway, there are those relations that you're not expected to absorb, because I'm not going to really do the calculations, but I want to tell you how it all works. So the only invertible element in that monoid is the identity. And so the core groupoid is just a discrete category with one object. And it's pretty clear that the linearization of our monoid is not Morita equivalent to the linearization of the terminal category. So I'm using prime usually to mean the complement in most of this talk. So this is, if you leave out the iota, you just get a semigroup, of course, from a monoid. And the amazing thing is that, well, I guess monoid people have been knowing this for ages, but having linearized after throwing away the identity, you still have an identity popping up. You need to be able to add and subtract. In this particular case, the identity element is what I'm calling L of C, which is sigma naught plus sigma 1 minus epsilon. And I don't expect you to see that immediately, but that's pretty easy calculation with all those relations that I pointed out. So there's the principle that you've taken a monoid, thrown away the identity, linearized, and there's an identity in there. Again, kind of amazing to me. So let me look at this example a bit more to show you why this groupoid suffices. We're going to see that fact that I just said about the identity is really important for why the groupoid suffices, but this is a bit of a different approach. So these are idempotents. There are a bunch of idempotents. It's easy to check those things. There are idempotents. Sigma naught and sigma 1 were idempotents. Tor, I guess, is too. And anyway, these are these particular modified idempotents. It's a standard process which you have for getting a complete set of orthogonal idempotents. And so that means that each one of them is idempotent, and the composite either way of one with the other, different ones, is 0. And so if you throw in the splitting of idempotents and freely adjoin direct sums, then you can say that this C is actually isomorphic to E0 plus E1 plus E2 plus E3, where these EI are the splittings of the idempotent EI. So you break the, we're now in a nice linear category by adding finite direct sums and idempotents, and so this C breaks up as a direct sum like that. However, when you do that, so you think that, oh, okay, we've our original monoid is Morita equivalent to 4 copies of V, maybe, but it's actually Morita equivalent to 3 copies of V, because E1 and E2 are actually isomorphic. They're not isomorphic back in delta bottom, or where, no, don't really exist in delta bottom, or even delta bottom. They do exist in delta bottom with the idempotent splitting, But then you need, if you've got a subtraction and addition, you've got this isomorphism between them, which I call gamma and delta. You can use these relations to see that these gamma and delta are actually morphisms of the idempotents, and that the E1 and E2 are actually isomorphic. So C is isomorphic to D plus C plus C plus F in this category of the Cauchy completion category. So a bit more detail. If you transport those endomorphisms, sigma naught, sigma 1, and tau, there's work to do here. It's not that much, but it's routine. Transfer for further sigma naught from C to C across to that morphism of that direct sum, and you represent morphisms, endomorphisms of the direct sum by matrices. Then sigma naught corresponds to that first matrix, sigma 1 to the second one, and tau to the third. And you can check that the relations are all satisfied and so on. And then if you check what it means for an endomorphism of the direct sum to commute with those three things to be an actual morphism in the Cauchy completion, you find out that the F has to be just a direct sum of 4 morphisms. F naught going from D to D, F1 going from E to E, and that the two middle ones have to be forced to be the same. F1 goes from E to E, and F2 goes from F to F, and it's just a direct sum of 4 things. So anyway, that shows you an explicit formula for why the linearization of this particular monoid is Cauchy equivalent to a product of 3 copies of well, no, it's Cauchy completion it's Cauchy equivalent to the linearization of the discrete category with 3 objects. In other words, the representation category is just V cross V cross V. Okay. So now I want to just show the setting that I've come up with, coming a lot from Dan Kuhn's paper, in which his example was that F was the category of finite dimensional vector spaces over a fixed finite field. That was what his F was, and he showed that that was that a groupoid sufficed for that. And the groupoid, of course, is what I'd call the finite general linear groupoid. Okay, so we need a factorization system. So this is just kind of revision for category theorists. They know all this stuff. A factorization system means that, well, they're closed under composition. There's one fact about them, each of the classes. The E's are like epimorphisms, the F's are like monomorphisms. That's why we use E and M. And they're closed under composition. The intersection is the invertible morphisms. They have this diagonal fill-in property that if you have a commutative square with a, well, from the way factorization people do it is a bit different from the way the homotopy theory people do it now. They put the morphisms left and right, but we put them up and down. So if you have an E at the top and an M at the bottom and a commuting square, you have a diagonal going from pointing down in the southwest direction, and that every morphism factors as an M and an E. So these are fairly standard things. The intersection is what I'm going to call G. It's the invertible. Well, it turns out the things in E and in M are all invertible, and we'll call that G. And I'm writing M prime, E prime, and G prime for the morphisms of F that are not in M or E or G, respectively. So this prime is just the complement in F in the sets of morphisms. And I'll identify the categories E, identify the sets of morphisms with the categories with those morphisms and all the objects of F. We also need it to be a proper factorization system, which means that everything in E is an epimorphism. It might not be, E might not be just the epimorphisms, but in a lot of examples it is, and in concrete examples they're just the surjections. And M is, the things in M are supposed to be monomorphisms. And the thing, you have this extra property in a proper factorization system that if HF is an M, then the F is an M. Like injective functions, one-to-one functions have that property. And so do epimorphisms or surjective functions have the other way around, that if FK is in E, then F is in E. So now it's a bit more technical category theory, I guess, but this is the part that is, I suppose, has its origins for category theory anyway in Marita Bunga's thesis, which was on, well, she didn't call them pre-sheaf categories, but basically it was about pre-sheaf categories of set-valued functors. So I'm taking V-valued functors, which are just R-module valued functors. And so there's this bi-category, which has as objects V categories, that's just R linear categories, small ones we take. And I think of them as R algebras with several objects. One object, R linear category, is just an R algebra. And the Hom categories of this bi-category are just what I'd call the left A, right B modules. So there's an action of A, well, anyway, they're just really V-functors from B op tensor A, where the tensor product is the R linear category with the Cartesian product of the sets of objects, and then the tensor products of the Homs. And I call an object of that Hom a module from A to B. Levere was calling them bimodules from A to B. Benabou first was calling them profunctors from A to B, and then changed to distributors from A to B. And Marita Bunga had them in her thesis for V equals sets, and just didn't give them a name. So the point is that these particular Hom categories are all abelian categories, abelian R linear categories. And so you can talk about short exact sequences, and so on amongst the morphisms. The two cells, the two-dimensional morphisms between the modules are just module maps. They just preserve the actions on either side. And composition is given by like a tensoring process, just like it is for tensor product of ordinary modules over rings, but non-commutative rings. However, you have some objects around, so you've got that integral sign involves taking a co-product of all those objects over B, and then doing an identification, which is just like the identification in tensor products of modules. In particular, if you have a little co-span like that, or a diagram of V-functors, you can get a module by taking this Hom process. So the value of that Hom at BA, there's a little bit of twisting over here. When it goes from A to B, then the B is in the first place in this part here. If you can see my pointer, you swap them over like that. Anyway, that's like a Hom. And then in particular, when one of those functors is an identity functor, you get for every functor you get, for every functor you get a module, one going from A to B and another one going from B to A. And in a bicategory, you can talk about what it means for a morphism to be adjoint, one morphism to be adjoint to the other, using the definition of adjunction and using units and co-units, which are just becoming two cells. And so it turns out that for every functor, you get an adjunction using these two modules, one going from A to B, the other going from B to A. And we've already said what Cauchy complete means. It means that they have the same completion with respect to both splitting idempotents and adding finite direct sums. And in that case, if we've got a Cauchy complete R-linear category, then any module with a right adjoint from A to B is isomorphic to one of the form F lower star. So functors sit inside nicely amongst the Cauchy complete categories. And small categories are quite often Cauchy complete, and big ones, if they've got any limits at all, are pretty Cauchy complete. So what I wanted to do was to try and so there's an inclusion of the groupoid in the core groupoid in the original category, something from G into F. And you might think that that induces the equivalence between representations of G and representations of F. And it'd be nice if it does, and sometimes it does. But in that first baby example, it doesn't. The actual equivalence is not just restriction, using restriction. And so it'd be nice if that the equivalence was some kind of sub thing or retract of the restriction. And that's more what is the case. So I wanted to use this lemma that if you have in this bicategory R an adjunction, and then you take and then you have an idempotent on one of the morphisms in that adjunction and split the idempotent, then you can get an adjoint to that splitting by by transferring, getting an idempotent on the original adjoint and splitting that. I hope that's clear. I mean, the lemma looks pretty complicated, but I write it down there because we not only need that fact, roughly speaking, I'm saying that if you've got an adjunction and you've got a splitting of one of the morphisms in that adjunction, then you can get a splitting. You can get an adjunction for that splitting, an adjoint for that splitting. But I'm needed in the write-up of this to actually have an explicit expression for what the unit and the co-unit of that new adjunction are. So there's a bit of an analogy here that with analysis of some kind, that these modules, taking the view that these, and this was originally, I think, Unade's idea for the integral notation for composition of modules, that there's an analogy with analysis. It's a bit like an integral, and you do have these kernels. So if you have a module from A to B, then it gives you a functor from the representation category of B to the representation category of A, using composition of modules, but more explicitly, you have that explicit, you have that integral formula. And so that's a way of going from this bicategory into or linear categories. So each object of R it's a V category already, but then I move it over to the category of representations in the VCat. Maybe I should write a big cat for that, but I'm not really emphasizing size problems today. Yeah, so this H hat has a nice, the H hat is a kind of tensor ring. I mean, there's a kind of, in Freud's little book there's origins of this. You call them tensor products of functors, the same kind of thing there. So the adjoint is a kind of Hom. And there's the formula for it. So you get this H tilde of F, where F is going from A to V. The value at B is the object of natural transformations from HB blank to F. Yeah. I guess it's a little bit technical here. So here's this inclusion that it would be very nice if that induced the equivalence on representations, but at least it exists, and it has because it's a functor, it's got this J upper star, which is the module given by J upper star of AB is the Hom RF of JAB. Remember, A is coming out of G and B is coming out of F. And the little lemma is that you get, well, first of all, the composition. So remember, M prime is the things that are not in M and the linearization of them. So we're looking at R modules with a basis, free R modules with a basis of the non-M maps from A to B in that top left-hand corner of the square. And what I'm showing here is the composition. Because of the proper factorization system, the composition on either side from A and on B restricts. And so that M prime is actually and I'm writing straight M prime to be the linearization, but it's actually a module just with composition. But then when you take the short exact sequence like this, I'm writing M for that. It does turn out that the MAB is the R linearization of the M morphisms, but you've on the effect on morphisms, you see you've got to it's composition if the thing does land in M morphisms again. And it's zero if it doesn't. So that's the way that bimodule M works. And everything, all the assumptions I put on the F and the G and the M, the script M and the script D, the factorization system, are self-dual. And so you get a similar thing with E prime is the linearization of the E maps. Or the surjection type things. So now you've got modules in both directions. There's an M from RF to RG and an E from RG to RF. And basically all you have to remember is that they're coming from the factorization system. The M comes from linearizing the factorization system M's, and the E comes from linearizing the factorization system E's. At this stage, we haven't proved their inverse equivalences or anything, but and they're not in general. But the little warning is that on morphisms, you've got to be a bit careful because they give zero sometimes. And you have to linearize to get this all to work. You can't just stick with the original F and G. Well, it turns out that if you compose the module E and the module M without any further assumptions, you do get the identity. So in one direction, M composed with E is the identity, and that's the easy direction because that composition of modules on the bottom of the page there, the M composed with E, you're integrating over the F. The F's got plenty of room, so it kills off quite a bit, and so you're able to get this isomorphism, which is basically coming from composition. This phi thing is like composition, except you have to compose when it lands in the right place and give it zero when it doesn't. Anyway, I hope you're getting a bit of a smell for the sort of mathematics that I've made this into. So because the hat process is a pseudo-functor, it takes adjunctions in the bicategory R into adjunctions in VCAT. And so you get that E hat composed with M hat is actually the identity. So one way round, you're getting a composite which is isomorphic to the identity. To get an equivalence, you need the other composite to be isomorphic to the identity, and that's the hard step involving an induction with a few more assumptions. Some of the processes you can, well, since you've got this isomorphism from E hat to M hat, you actually get a natural transformation big theta from M hat to E tilde. And there are a bunch of processes that you can use to show that that's an equivalence, or an isomorphism, actually. If you look at it the right way, it turns out to be a matrix, and you can find a time when that matrix is actually a upper triangular matrix with identities down the diagonal and zeros, well, zeros below the main diagonal and identities down the main diagonal and other stuff. And because you're linear, that means it's an invertible matrix. So it's worth looking at the case when theta is invertible, and then at least you get that M hat is fully faithful. So that which way does M hat go? That means that the M hat goes from mar G, representations of G, to representations of F. So the way you might expect the subcategory, the smaller thing is a subcategory of the bigger thing. So there are all those observations. Particular M hat and E tilde, you know, the hat and the tilde process work for any module, but because we've got special M hats and E tildes, you might be interested in looking at the object of subobjects of A and the object, or the ordered set of subobjects of A and the ordered set of quotient objects of A, quotient and sub in the M sense and the E sense. And probably the easiest way, rather than looking at equivalence classes, is to choose, using a big axiom of choice, representative sets. And so by sub A, I mean a representative set of M subobjects of A. And then you can rewrite the coends and the ends. The coend is a big sum, gets replaced by a big sum, as shown there. So it's just a sum of the values of T over the subobjects. And similarly for the E. And there's a little description of a process, a possibility if you can order the subobjects. If you've only got finitely many, for example, and you can order them, of a way of getting a matrix of the sort I described before, a triangular with identities down the main diagonal. How's my time going? It's okay, so probably I shouldn't spend too much time on going through these examples. Oh, this might be of interest. This is an example that's appeared in various places in the literature. So if you take A to be any category in which every morphism is a monomorphism, and where pullbacks exist. So you could take, for example, delta with the injective morphisms. And if you have that each slice category so has finitely many isomorphism classes. So because everything's an M, a monomorphism, that's like saying that you only have finitely many subobjects of each object. And then you take F to be what's called in the literature a sharp, to be the category of spans in A. You can think of them as partial maps because they're spans where each leg is a monomorphism. So they're kind of partial injective maps, what you feel like, or partial monomorphic maps. So they're spans. Well, I call it the category of span. So the objects are still the same objects as A, and the morphisms are diagrams like this, but only taking isomorphism classes of them. And you compose using pullback. It's a familiar construction to category theorists, the category of spans in another category. And the bicategory of spans was one of the main examples that Benabou had in his first book, first paper on bicategories. So you take M to be the spans where the F1 is invertible, the left-hand side, and take E to be those where the F2 is invertible. And all the machinery applies. And the core groupoid here of this particular F, which is the A sharp, is actually isomorphic to the core groupoid of A. And an example of this is what a lot of people, particularly in algebraic geometry, in algebraic topology, call Fi, which is the category of finite sets and injective functions. And then you've got F being Fi sharp. And in this case, G is the groupoid of finite sets and bijections. It's the usual, I call it the symmetric groupoid. A lot of people would call it that, I think, because the endomorphism monoids are the symmetric groups. And the category of representations of that is the category of Joyal species, or R-linear Joyal species, which is a product of categories of R-linear representations of the symmetric groups. And so you deduce this equivalence between Joyal species and the representations of that particular category of spans of finite sets and injections. And Purishvili, I might have left out a letter there, had that in 2000, that particular thing, and various people from Chicago rediscovered it in the context of algebraic topology and stable homotopy theory and things. Yeah, I hope everything's going all right. I'm only seeing my own screen here. I'm not really seeing any people. So is everything all right, Nossen?
We're all here. We're all here. It's very good. Very good. Are you going to do more examples, or are you going to go on?
Yes. I think so.
Maybe I just make a brief comment that essentially this result about spans of injectives is really essentially the semi-simplicity of inverse semigroup algebras, which in semigroup theory was known in the 1950s, except they look at the finite versions of these, but the same proof would work for the infinite versions too.
Right, yes, so this method of getting matrices, well, I learned that from Ben, that this was all in the semigroup theory and sort of in the finite cases. Yeah. And it's got that. Anyway, I'm going to acknowledge a few things at the end if there's time. But okay, so I want to apply that lemma on retractive junctions. And so we want to show, if we do want to show that the M from RF to RG is an equivalence in the bicategory R, if it's going to be an equivalence, it's going to have an adjoint. To have and be an equivalence, the equivalence can always be made between the adjoint morphisms by adjusting the units and the co-units. And so N will have to have a left adjoint. So you'd like to apply the lemma to get the left adjoint by splitting an idempotent on J lower star, because we've already got the J upper star is related to M. There's a map from J upper star to M. And that would mean that you'd want M to be a retractive J upper star. And so I had that short exact sequence. Remember, it had M prime, J upper star, and M. And you'd want the Q, which went from the right-hand side of that short exact sequence, going from J upper star to M, to have a splitting. that epimorphism should have a splitting. And that splitting, well, Q itself is natural in everything, but you want that splitting to be natural in A lying in G and B lying in G. And particularly, you want it natural in B. And so by Unida, you can take, if it's coming back from this Hom on the right-hand side, RFAB, which is a Hom. The M is a kind of Hom, but it's as I say, it's not just by composition. You often have to make its value on morphisms equal to 0. So the right hand is a genuine Hom, and so wanting a map back the other way, you're going to take B equal to A and evaluate. Well, actually, the left-hand side is a Hom. The M is a Hom if you restrict the B to lie in Rn. Yeah, okay. So then you take B equal to A, evaluate, and you get row AA of the identity, and we're calling that P. And so P is actually something from A to A, and by using Unida, it tells you that your splitting row is of the form multiplying by PA. That's all part of Unida, the Unida lemma. So anyway, what I'm trying to get down to is, if you want to use this lemma on retracts of adjunctions, then it's natural to come up with this idea that there should be idempotents around, or at least these morphisms PA from A to A. It is actually an idempotent. So yeah, I'm using P for this thing because I didn't want to use little e because that looks like something coming out of E or an idempotent, something that we've already looked at. Anyway, here's the axiom, which is really just taking the properties that Dan Kuhn used in his paper and just formalizing them a bit. So suppose that you've got this category F, and for each object, there's a morphism, not in the category F, but in the linearization of the category F, such that it's an idempotent. When you compose something that's not in M on the left with P, with a P, you get 0. When you compose on the right with something that's not in E, you get a 0. It should be natural, the P's should be natural with respect to invertible things. Well, the G's, the things that are in both E and F, which is E and M, which is a little bit more restrictive than just invertible in the general case, but it turns out most of the examples, they are just invertible things, and G is the core groupoid. Oops. And this is the big one, right? This P4 is the complement idempotent. The one, if PA is an idempotent, then 1 minus PA is 2. And what you're asking is that this should be expressible as linear combinations of things that are both not in B and not in M. That might be a bit hard to understand, but that's the case. Now, the point is that if you started off with an F, which was actually a groupoid, then you could take F to be E and equal to M to be G, and the PA to be the identity. So what I like to think is that this P prime is a kind of obstruction to having F a groupoid. But when you have these idempotents, the general thing's not very far away from being a groupoid anyway, because we get this core suffices property. So that's a rather trivial example. I think I'll have some more substantial examples later, I hope. So you use those P's to get a retraction sigma. So if you look at the square there, we've got the inclusion of the non-M things in F, and we've got now this, using those properties, you get this diagonal sigma, which is that diagonal is really just saying that you've split the idempotent, right? So P prime, the vertical arrow on the right, this one here, if you can see that little marker, is an idempotent because P prime's an idempotent, and this is composition on the right with the idempotent. And so it's an idempotent. And so now we've got a splitting of it, and we can use that. Well, that with the splitting and the idempotent coming from P prime, I'm calling pi prime. And so there's a pi, which is actually 1 minus pi prime, which is composition on the right with PA rather than with PA prime. And so we get, this is moving over from sort of the left-hand side of the short exact sequence to the right-hand side of the short exact sequence. So you get this splitting, that M is actually a retract of J upper star. And that the action that looked a bit funny before, because it was 0 sometimes and not, and still is, but it's obtained at least by putting a G on the back and the F on the front of the M, and then composing with one of the idempotents, which does all the damage in giving the 0 sometimes. So this is just on the other side for the E's. So you also get that E is a retract of J lower star. So that's all okay, I hope. Now there's a few things here. Oh, this is just, the lemma there is just saying that we're in good shape for applying the lemma, because it turns out that the pi and the curly pi are actually mates, meaning that was one of the requirements in that lemma. And so from all that, you get that M hat and E hat are adjoint, and that M tilde and E tilde are adjoint. And so because we already know that for any module, the tilde is always right adjoint to the hat, that means that, and we've got we've now got an isomorphism, but what have we got? That M tilde is, has right adjoint E hat. So E hat must be isomorphic to M tilde. So yeah, we've got these two adjunctions which are between the FG and the F, the RG and the RF. And basically from that phi isomorphism that I had before, we do get that the unit of the adjunction back in the bicategory R is invertible. So you've got E is left adjoint to M back in the bicategory R, and this is all under the assumption of that idempotent assumption on the category F. So it's a bit technical, but anyway, the isomorphisms are basically coming from the phi bar isomorphism we had before. That comes in the sort of reverse direction here. The co-unit turns out to be inverse of the phi bar. But the hard lemma is the other way around. And that is by induction. And it's not quite in Kuhn's paper, although he makes all the right noises, but I found that a little bit of a gap that I took a long time to overcome. And luckily, he answered my emails and helped me out. So he knew all the stuff, it just wasn't quite in the paper. So you have to sort of creep up at the, oh, well, you've also got this extra assumption, not only the idempotent assumption, you've got the assumption that each object only has finitely many M subobjects. Well, that's all. And then the co-unit of that adjunction. Well, this is only, it's a split epimorphism. That's what you get from this induction that I'm just about to give you the idea of. You only get that it's a split epimorphism as an object, as a morphism in R, or two morphism in R, it's a split epimorphism. But it's actually an isomorphism. And that's kind of classical Morita theory. Okay, so the co-unit, it turns out that that co-n that you see there in the proof is actually isomorphic to that R linearization of the Holm in F from A to B. I guess this is a bit technical, but it is isomorphic, but the isomorphism that exists there, which is one that exists with any factorization system, more or less, is not the co-unit. And that was what was holding me up understanding Kuhn's paper. This is what the co-unit is, and I couldn't see why that was invertible. So you have to do some more work. So the only way I could put half a proof on this page and half a proof on the next page was to put an end of proof sign on and carry over. But it's not, that's why I say it's to be continued. It's not the end of the proof. So really what you do by induction is to show that the identity element of A is in the image. And you creep up to it a bit by only, you order the isomorphism classes and you take this phi bar, and anyway, but the main point is once you've got the identities in the image, then you can take something that goes back the other way, which is going to be natural by your Nader's lemma. If you know where the identity goes, you're okay. So, so if you have something that goes to the identity, then you can get something back the other way that goes to that. And this gives a right inverse to the co-unit. Yeah, and so similarly, you could do the whole thing in B, and with the E, and you end up getting the co-unit as a natural right inverse. And to get the last little bit, well, one way that I can do it anyway is to refer to a paper I did with Brian, which was about strong generators being dense. I mean, this was a paper we wrote when we realized that if you have a topos, we'll say Grothendieck topos, then any generating set of objects, any set of objects which generates is actually dense. It means that every object in there is a co-limit of, in a canonical way of, so we wanted to look at categories where strong generators were automatically dense. And this is a situation where that's true. These are Grothendieck abelian categories we're dealing with, basically. And so that theorem from the paper with Brian Day applies. And so you get this equivalence of RF and RG in R. So in the terminology of ring theory, you'd say that RF and RG are Morita equivalent several object R algebras. And in terminology of enriched category theory, you'd say that RF and RG are Cauchy equivalent V categories. So the M hat's an equivalence with inverse E hat, but you've got this other equivalence M tilde with E tilde. And M tilde is actually a retract of restriction. So that was one of the, as I say, it would have been nice if restriction was the equivalence, but now some retract of it is. And that means that if you have, not only do you get the equivalence, because we're doing it at the level of the Cauchy completion, the completion with respect to splitting idempotence and finite direct sums, it doesn't just work for V, the category of R modules, it works for any category you want to take representations of F and G in. Right here. Okay. So anyway, that's another. You can take representations in any category in which idempotence and split and finite direct sums exist, and you'll get an equivalence. Yeah. So I'll probably go a little bit strange here, but I'm calling a morphism the category stiff when the only endomorphisms of A through which F factors are automorphisms. So in other words, if you have that F can be written as an endomorphism composed with another map, then that endomorphism has to be invertible. And you call it co-stiff when it's stiff in the opposite category, and the category stiff when it's both, when the co-stiff things are the E's and the stiff things are the M's. So in other words, the co-stiff and the co-stiff form a proper factorization system. So one of the consequences of this is something that I think it's the origins of all uniqueness implies existence theorems, this pigeonhole principle that in a stiff category, if you have an M, which is an endomorphism, then it's already invertible. So, or if it's an E, if you've got an E going as an endomorphism, then it's invertible. So, for example, that's the usual pigeonhole principle is for right. If A and B are isomorphic, then being surjective is the same as being invertible, is the same as being monomorphic. So the part of Kuhn which is not self-contained is that he does actually refer to the result of somebody who spent most of his life in Australia, in Canberra, Lotzi Kovacs. He died about 10 years ago. But he found there's a history to this too, and Steinberg Ben has helped me with some of that history. Some of it's in Kuhn's paper. That if you take this particular example of F to be the category of finite, you can say finite because finite dimensional is the same thing for vector spaces over a finite field. You fix your finite field, take vector space over a finite field, and if you look at the endomorphism things in there, and linearize, and then you just take the non-invertible things. Well, sorry, I linearized a bit early. You take the non-invertible. So what am I talking about? You've got the groupoid, the group of matrices, if you like, or linear endomorphisms of a finite dimensional vector space over a finite field. And that's a nice monoid. And you take the non-invertible things in there and you linearize. Then what Kovacs showed, by quite a clever process, I think, that there is an identity in there. So you've taken the non-invertible things, linearized, and again, so it's like that example right at the beginning. You have to linearize. The difference is that that you do need not only to have the linearization, you do need to divide by the characteristic of the field. So there's a restriction on R that the characteristic of the field should be invertible in R. So if you have a Kovacs idempotent in the general setting, then you do get this idempotent axiom holding. That's the point of this. it turns out you've got these properties that the Kovacs idempotence automatically a central idempotent, and the components of a natural endomorphism of the identity functor of the groupoid. Anyway, then you'll let PA be 1 minus LA, and everything's satisfied for that idempotent axiom. So that's probably the only main example I have here, but all the examples from our Dold-Kan paper fit in too. And Ben Steinberg pointed out that this is all about semi-simplicity, or can be a consequence of semi-simplicity as well. That if so you see, you only need these idempotents on each object. It's kind of interesting, and using semi-simplicity, the way, probably the main point about semi-simplicity is that the representation categories, short exact sequences split in those representation categories. So if you take any category of finite any finite monoid of Lie type in the sense of Butcher and Omninsky, then that has this property that this thing's semi-simple. And Steinberg's nice book gives conditions on any finite monoid such that the linearization should be semi-simple. And one of the things that's this, it's kind of a Mashka property. You need the Mashka property there. Okay, so there's a little description of why semi-simplicity is enough there, but it's basically because idempotent split, so you can get the these Kovacs elements. So that's pretty much it. I gave a talk when it was a bit too early in the category seminar, and Alexander Campbell pointed out a few gaps in the talk, and that led to my discussions with Nick Kuhn, and he was confident in his theorem all the way through, and I kept jabbing him and got more information and turned it into my language, I guess. And of course, Kuhn actually pointed out Ben's book, and then Benjamin wrote to me too after I put the preprint on the archive. So I hope my watch is right. It's been.
It's perfect. It's perfect.
Okay, still okay.
Okay.
Yeah. Yeah. So thank you to all of those, and I think I'll leave it at that.
Okay. Thank you very much.
Thank you.
It's a lot of stuff. Any questions? Any discussion?
Yeah. I'm sorry about all that. I knew it was going to be long, but it's
good.
Yeah, well, I was a little bit nervous about giving it in front of Ben because he's an expert on this stuff.
It was a very nice talk, Ross. I'm going to actually have to leave pretty soon. But it was
okay.
Very nice talk.
Well,
I mean, a lot of things you write down look very familiar to me. I don't really understand bicategories very well, but when you actually write formulas down, they look a lot like what we do. I wrote you a quick email, but I think somehow what we do in semi-group theory is we just take the Cauchy completion of the monoid, and then we take its like split epis and its split monos, and we build bimodules out of those, and we relate them to the groupoid of that idempotent splitting. And I think that's essentially how we're connected to what you're doing. But I'm not 100% sure, but that's what it seems
sounds
like.
Right. No, that sounds right. Yeah.
We have different names for all this stuff, but there's some lemma that says that what we call L classes correspond to either split epis or split monos, but I can never tell which direction things go inside the idempotent completion and things like that. And then the groups that we look at are the automorphism groups and the idempotent splitting and these kinds of things. And I think our main kind of result is if you have a von Neumann regular monoid, then the groupoid suffices for the Karoubi envelope of that monoid precisely when the monoid has a Frobenius algebra.
Right. Yeah.
Which is what happens for Mn over a finite field and good characteristic.
Right. Yeah. Yeah, so yeah,
But it's a very nice talk. I really liked it.
this is familiar to category theorists that that there are different names for things. When we discover that something we've done is connected to another field, and the other names are there, and quite often the other field has done it well before us. Yeah. Oh, it's been fun.
Yes.
I've enjoyed my conversation with you, Ben.
Okay, well, it was nice also talking to you, and nice to I don't even have my video on to sort of meet you in person as we get these days. But I will have to run now to it.
Yeah.
So very nice to talk. Thank you.
Thank you.
Any other comments? Any other questions? Okay, anyways, let's thank Ross again. Thank you, Ross. It's a pleasure. Just again, I want to advertise next week we're meeting in person. So if you can, if you're anywhere near New York City, try to come over. We need a group there. But if not, we're gonna tape it and then we'll put it online.
Oh, okay. We can do that.
I had a more general question for
Please.
Ross. You mentioned profunctors and distributors or modules, whatever they're called these days. Do you know the work of the Japanese category theorist Takahiro Kato? Does that ring a bell?
Yes. Probably John Power would know better than me. We have John Power at Macquarie University too, and he's spends a lot of time in Japan. I don't particularly. What work are you?
Well, he's developed a book manuscript called Modules and so he uses that language, Modules and Universal Constructions, as sort of a new approach to category theory in general. And you know, it's book length, and I've urged him to get it published, and he's such a perfectionist that he changes something every few months and then puts it back up on one of the websites. But it's over my head to judge whether he's, whether the book is really good or what. But it's taking the notion of profunctors really being basic, or module, as he calls it, and developing category from that point of view. And he gets a lot of seemingly new results about universal constructions and so forth. I can send you the book.
You can send me his name and or an archive address or something,
yeah,
if it's in the archive. It's probably likely that my Japanese contacts would know.
But he seems to sort of work alone, and I
don't
know if other people know it.
Is he in Kyoto or Tokyo?
No, his name is Kato, Takahiro Kato.
No, do you know where he works?
No, I actually don't know. I don't remember. I'll send it to you.
Anyways,
Thank you.
Anyways, thank you very much. Let's
stop
the recording.